Alright, so this is the third video for the final review, and we're looking at problem number 6 here about average and instantaneous rate of change. Our function is the square root of 2x minus 3. The average rate of change on the interval from 6 to 11, which is what this says, is going to come from the function evaluated at b minus the function evaluated at a over b minus a. That's our formula for average rate of change. So we're going to have the square root of 2 times 11 minus 3 minus the square root of 2 times 6 minus 3 all over 11 minus 6, which is the square root of 19 minus the square root of 9 over 5. You can approximate that or leave that exact. Instantaneous rate of change comes from taking the derivative and plugging 6 into it, because it says when x is 6. So because our function is to the 1/2 power, our derivative will be 1/2 2x minus 3 to the negative 1/2 times 2. Or just 2x minus 3 to the negative 1/2. So when we plug in 6, we get 12 minus 3 to the negative 1/2, which is 1/3. That's the instantaneous rate of change when x is 6. Moving on to our optimization problems. Remember, for optimization, we had to figure out a primary equation, a secondary equation, and then we used our secondary plugged into our primary before we took our derivative. So primary equation for this situation is what I'm trying to maximize, which is air volume. We've got a box with a square base, and so we can use the dimensions x and x for the base because it's square, but we'll have to use a different dimension for the height. So I just took my box and flipped it over on its side, and what I want to maximize about my box is volume, which is x times y, length times width times height. So the surface area in my box is supposed to be 108 square inches. And what that means is my secondary equation is 108 should equal the amount of material it's going to take me to make the bottom, not the top because it's open. So that's x squared, plus the amount of material to make each side. Each side is x times y, and there are 4 of them. So my surface area is x squared plus 4xy. So the next step is to do a substitution. And if I want to do a substitution, I need one of my equations to say x equals or y equals. That's the secondary. And I can easily solve for y if I subtract x squared from both sides and divide by 4x. So my secondary equation can transform into y equals 108 minus x squared over 4x, and that can get substituted into my primary equation so that I have x times 108 minus x squared over 4x. And that will give me x is divided out. The divide by 4 could be 1/4 times instead. And then I could distribute my x in. And so the easiest thing to take the derivative of is 1/4 108x minus x cubed. And then I can use the constant multiple rule and get the derivative to be 1/4 108 minus 3x squared. So my critical value, or critical values, but only one of them I'm going to be able to use, is when 108 equals 3x squared, which is when x squared equals 36, which is either plus or minus 6, but not minus because 6 is a length and I can't use minus. So now I'm going to try to prove that this value of 6 is actually going to maximize my volume. And so I'm going to do that by taking the derivative of the derivative and seeing that it is going to always be negative when I plug a positive number in, which means my graph is always concave down, which means the only thing I could have found is a maximum. And that's going to occur when x is 6. And now I need my y value, so I've got to go back up to my substitution step to get that. And y will be 108 minus 36 over 24. And when I calculate that, I get 3. So x equals 6 and y equals 3 will be the way I maximize this volume. The second maximization problem is about fencing. So this is a little bit more in line with business calculus class in terms of cost. The other one was more of an engineering kind of example on how to maximize volume, but this situation I have an area I want to fence in, and the thing is the cost per foot depends on whether I'm doing the width, so we'll call this the width, that's $3 for every foot, or the length, which is $6 for every foot. So if I call the width x and the length y, I can come up with a way to express the amount of money that I'm going to have to pay to fence this in. So that amount of money is my primary equation. That's what I'm trying to minimize. So if I made this side and this side of the fence, they would both cost $3 per foot. So I would have 3 times x and another 3 times x, which would be 6 times x, and that would be the amount of money to fence the widths. So the lengths cost a different amount of money, and that might be because there's a door in them or something special about them that makes them more expensive. So for every y here, I'm going to have to pay $6. So since there's 2 of them, it's going to be $12. And that's a formula for my fence expense. But my secondary equation comes from this number 3,600, and that's the area I'm enclosing, so I know that length times width has to equal 3,600. Which means I know that if you tell me what the width is, I can tell you what the length is. So this is going to be what I'm going to use in my primary instead of y, so that I can take a derivative. So my substitution step is the fencing is 6x plus 12 times 3,600 over x. And that means 6x plus, I'll take 12 times 3,600 and get 43,200. And then x to the negative 1. So the derivative is 6 minus 43,200 x to the negative 2. My critical numbers come from factoring out. So I'll factor out a 6 and the lowest degree on x. And I'll be left with x squared minus 7,200. So 0 is a critical value. 0 makes no sense in the problem, so we'll throw it out. x squared equals 7,200 means that x could be the square root of 7,200, which is 84.85, or it could be the opposite of that, but not in this problem. So let's check to see, or prove that this actually is minimizing my cost. So the proof is going to come from the second derivative. Whether I'm concave up or down is going to tell me whether I minimized or maximized. So my second derivative is the derivative of my first derivative. So that is 86,400 x to the negative 3. And when I plug that number in, it's positive, concave up, so I must have been a min that I found when x was 84.85 and y was 3,600 divided by that, because that's my connection between x and y. And so 3,600 divided by that is 42.43. So those are my optimization problems.